Assalamu alaikum dear students. This is our sixth lecture of group 3-2. Uh, here we are going to discuss P group. So first we need to define what we mean by a P group. Remember in P group P is a prime number. P is a prime number. And also one thing is very important is that we are going to discuss finite P groups. Okay. So what is the definition of a P group? Definition: let P be a fixed prime let P be a fixed prime. A group G is said to be a P group if the order of G is equal to P power alpha for some alpha greater than or equal to 1, right? If order of G is equal to P power alpha, where alpha is greater than or equal to 1, then the group G is called P group. Then the group G is called P group. Okay, so what is the definition? If you can express the order of a finite group G as some power of a fixed prime P, where power should be greater than or equal to 1, of course, then we say that G is a P group. Okay. One thing is very simple deduction is that every element of G, the order of every element of G must also be some powers of same prime P, because you know with the help of Lagrange theorem that order of element also divide the order of a group G, where G is a finite group. So since the order of G is P power alpha, and you know that which type of numbers can divide a number P power alpha, of course these numbers should be P1, P2, P3 and so on, P power R, where R is less or equal to alpha, right? So that's why it's a very simple consequence that when your order of your group is P power alpha, then of course the order of every element must also be the some power of the same prime P. Okay. So remark is, you can say remark that if order of G is P power alpha, where alpha is greater than or equal to 1, and you know P is a prime number, then the order of every element of G must also be some power of P, that is P power R, where R is less than or equal to alpha. So we will discuss with the aid of an example what I am saying. So the definition is, if order of a group G can be expressed on P power alpha, where alpha is greater than or equal to 1, then we call that group as a P group, right? So further we are saying that if G is a P group, then order of every element of G must also be some power of the same prime P, because you know that with the help of Lagrange theorem that order of element also divides the order of G. So if your order of G is, let's say 5 over 3, so if the order of G is 5 power 4. So then which numbers are the divisors of 5 power 4? You know that the divisors of 5 power 4 are 1, 5, 5 square, 5 cube and 5 4. And 1 can also be written as 5 power 0. Right. So this means that the element, if A is any element of G, then the order of A must be either 1 if it is the identity element, or it is 5 or 5 square or 5 cube or 5 4. So there is no possibility of order A as 6, because 6 is not a divisor of 5 power 4, and so on and so forth. So it's a simple consequence is that when the order of a group G is P power alpha, then order of every element of G must also be some power of the same prime P. Here P is the fixed. Here P is fixed, right? Okay, let's have some examples. First example is, if you say D4, this is order of D4 is 8, it's a 2 power 3. You know 2 is a prime, so D4 is a 2 group, right? And you know that what is D4? D4 is E, A square, A cube, and then B, A B, A square B, A cube B. You know very well. So what is the order? This order is 1, which can be written as 2 power 0. Its order is 4, its order is 2, and you know 4 is 2 square, its order is 4, which is also 2 square, its order is 2, its order is 2, its order is 2, its order is 2, and you see the order structure, that the element of every the order of every element of G is some power of 2. It's a 2 group. So D4 is a 2 group. Similarly Q8 is 8. This is also 2 group. So this means that there may be more 2 groups. There may be more 2 groups. This is also 2 group. This is also 2 group. And another thing is that whether these two are isomorphic to each other or not. Can you find that the isomorphism? Yes, they are not isomorphic to each other. That is D4. You have in Q8 all the elements other than identity have order 4 or order 2, but here only we have only 2 elements of order 2. Okay, so what is Q4? This is plus minus 1, plus minus I, plus minus j, and plus minus k. This can be written as 1 and minus 1. So if you see the order structure, its order is 1, that is 2 power 0. Its order is 2, that's 2 power 1. The order of both these plus minus I is 4, which is 2 square. Its order is 4, which is 2 square. Its order is 4, which is 2 square. You see, this is also a 2 group, right? You have some other examples. Okay, we have C125. C125, order of C125, cyclic group of order 125. You know, its order is 125, and this is 5 cube, right? The order of C125 is 5 cube, so it's a P group. Okay, so the elements of this group, the order of elements of this group are in fact 1, 5, 5 square, or 125, right? So it's a cyclic group of order 125, right? That's it. V4 V4 is order 4, which is 2 square. This is also another 2 group. So you see, with the help of these examples, you can understand that you may have more P groups corresponding to a fixed prime P, right? You have seen that V4 is a 2 group, and Q8 is a 2 group, and D4 is a 2 group, and there may be some other examples of P groups. C2 cross C2, C2 cross C2, its order is 4. This is also which is 2 power 2, which is 2 power 2. This is also a 2 group, and you know that the V4 is not isomorphic to V4 is isomorphic to C group 2 cross C2. Okay, we should not discuss this. It's simple. I should discuss C4. So I'm going to discuss C4, of course, which is equal to C2 cross C2, and what is C4? Order of C4 is also 4, that is 2 square. Okay, but C4 is not isomorphic to V4. This is isomorphic to C2 cross C2. So these are the different groups, different abelian groups of order 2, that is C2 cross C2, and one is the C4, which is not isomorphic to V4. With the help of these examples, we can see that you may have more P groups corresponding to a fixed P, and also you can see that these P groups are not isomorphic to each other. You may have such P groups corresponding to a fixed P, prime number P, which are not isomorphic to each other. This was the notable point of these examples. Okay, next is that so you cannot say that any two P group of same order are isomorphic to each other. No, we can never say. Like in cyclic groups, you love to say that any two cyclic groups of same order are isomorphic to each other. But here, in case of P groups, we cannot revise that result which we have established in cyclic groups. Okay, so we are not saying that any two P groups of same order are isomorphic to each other. Okay. Next idea is center of a P group. It's a very well-known result because we want to move towards Shillow's theorems, and we have some special results to prove Shillow's theorem. So one of the popular result is the center of a P group is non-trivial. What do you mean by non-trivial? Non-trivial means this center has more than one element. You know that the trivial center is the identity element. Identity is the trivial element, trivial center, because identity commute with all other elements. That's why when we are saying that center is non-trivial, this means that you must have at least one element in the center other than identity. Okay, so if you can prove that, if in a P group you have more elements, more than one elements in its center, then we can say that the center of a P group is non-trivial. Okay, so now we are going to prove this theorem. Theorem is center of a P group is non-trivial You can see with the help of examples. You know that uh, uh, which are the P groups. You know Dn. Dn is the center of Dn is E. You know the center of Dn is E if n is odd and E a power n by 2 if n is even. So look, this is D3, center of D3, you know, this is center of D3, right? Center of Dn, so this is center of D3. According to this center of D3, n is odd is the identity element. Center of D5 is the identity element. You know, the order of D5 is 10, so D5 is not a P group, right? The order of D5 is equal to 10, so which is not equal to some P power alpha corresponding to some prime P. So D5 is not a P group, and you know its center is the identity, the trivial center. However, when this is n is even, you are getting more than one element. This a n power n by 2. Can we check that there are some P groups in this story? You see, if you take center of, what is center of T4? You know D4 is a P group because order of T4 is 2 into 4, which is equal to 8, which is 2 power 3, right? It's a P group. D4 is a P group. It's a 2 group. So the center of D4 here should be E and A power 4 and 4 by, so you know, A power n by 2. It's a 4 by 2. This is 4 by 2. So the center is E A square, right? This is the center of D4. Similarly, you can find the center of D6. D6 is 12. The order of D6 is center of D6 is E A power 6 by 2, which is E A cube, right? But the order of D6 is 12, which is not equal to some P power alpha. So look at, this is the counterexample. We are not saying that center of P group is non-trivial. If G is a P group, then its center is non-trivial. However, if center is a non-trivial, you can never say that it is always a P group, right? So with the help of this discussion, we are getting another result is that this theorem, the converse of this theorem is not true and would never be asserted, right, in factoring journal. So we will never claim about its converse, because here you see that D6, the order of D6 is 12, which is not equal to P power alpha. However, the center of D6 is non-trivial. Its center has other than identity elements. So when the center is non-trivial, you can never say that it's a P group. However, if it is a P group, then center must be non-trivial. So let's have a proof. We know that the class equilibrium. You know the class equilibrium? Class equilibrium is actually the order of G is equal to the order of sum of CAI, order of sum of CAI, I varies from 1 to R. So this is the class equilibrium. Suppose there are all possible conjugacy classes in P group, in your given P group, then the class equation is order of G is equal to CAI, and you know that every conjugacy class is in fact the order of in the normalizer. of the corresponding element AI. So that's why the order of every conjugacy class is also being the order of normalizer is a divisor of this G. So and this G order of G is P power alpha since it's a conjugacy class, it's a P group. If order of G is P power alpha, and order of each conjugacy class also divides P power alpha. So that's why order of every conjugacy class must also be some P power, some powers of the same prime P. Okay, so we can have a better start that that the relation of conjugacy is an equivalence relation. So always defines the partition of the group G, and that's why you have equivalent classes. Let there conjugacy classes. Let there be R possible conjugacy classes, namely CA1, CA2, and CAR. Right. So we know that. We know that the relation of conjugacy between conjugacy on a group G. We know that the relation of conjugacy on a group G always defines a partition of G. So that's why you must have such classes whose union is the entire group G, and there is no intersection between them. So that's why you can have such a conjugacy classes, right? So let there be all possible conjugacy classes namely CA1, CA2, of course CAR. Of course, A1, A2, AR are the elements, the string elements of your group G, where AI belong to G, 1 less or equal to Y less or equal to R. Okay. Next. Such that CAI intersection CAJ is phi for all I is not equal to J, and G is equal to union of CAI I will from 1 to R. Okay, you can have conjugacy classes, say CA1, CA2, CR, which are defining the partition of your given P group. Okay, so that's why you must have G is equal to union of I will from 1 to R CAI. Then by exclusion principle, you can write its order. Then by exclusion principle, we have order of G must be equal to summation CAI I will from 1 to R, which is in fact the classic way. So this is number 1. or you can write directly that let G is equal to this be the class equation where CA1, CA2 are the disjoint conjugacy classes or possible conjugacy classes, namely R. Okay. Clearly, equation 1 is in fact the class equation of G, the class equation okay, this is our first idea. You take the conjugation relation on G, and conjugacy relation defines the partitions. So that's why you have this equation, which is also the class equation of 1. Now, since G is a P group, you may assume its order is P power n, and also that the order of every conjugation class, is in fact the order of the normalizer of AI, and normalizer is a subgroup of G, and its order must divide the order of G. So you may suppose that the orders of these conjugation classes are also P power mi, where I is from 1 to R. Okay, right. Since G is a P group, so we let order of G is equal to P power n, where n greater than or equal to 1. Also, we know that order of CAI is equal to index of normalizer of AI in G. Right. We have proved this theorem in our last lecture, that number of element in a conjugacy class is the index of its normalizer in G. So the order of this CI conjugacy class is in fact you first find the normalizer of AI in G, normalizer of AI in G, then its index in G. First find normalizer of AI in G, it's a subgroup, and index in G. And you know that by Lagrange theorem, since normalizer is a subgroup, so its order and index both divide the order of G. That's why CAI also divides the order of G, which is P power n. Okay. So since NAI index of normalizer in G divides order of G, which is P power n greater than or equal to 1, by Lagrange theorem. So for each I is equal to 1, 2, 3, so on. So we see that order of CAI also divide P power n for each I with some 1, 2, 3 and so on. And since each CAI order of each conjugacy class CAI divides the P power n, which was the order of G, so you now may suppose that order of CAI is equal to P power mi. So that's why we assume therefore assume order of CAI is equal to P power mi for each I is equal to 1, 2, so on up to R. Putting in 1, we get P power n is equal to P power m1 plus P power m2 plus so on plus P power mr. Number 2. In fact, 2 is the class equation of your P group, where P is any prime. Okay, so this is in fact the class equation of your P group. Okay. Also, we know that one of the PMI must be the identity. Suppose it is M1, because you know that identity is the self-conjugate element. So that's why in its class you are having no other elements. So conjugacy class corresponding to the identity element is containing just one element, which is E. But CE, the order is 1, so without any loss we assume Pm1 is equal to 1, then equation 2 becomes P power n is equal to 1 plus P power m2 plus P power m3 plus 1 plus P power mr. Right? This is equation number 3. Okay, another point is that question is whether there is only one element which is the self-conjugate element. No, this is not the case. In general, you may have more self-conjugate elements. And you know that all the self-conjugate elements are the central elements. So you may assume that there are more self-conjugate elements. If there is no self-conjugate element other than identity, we would have a contradiction. That's why there is no hesitation at all to assume that there are, suppose, k self-conjugate element, or there suppose k number of self-conjugate elements. Of course, if you prove that k is greater than 1, of course 1 is this, and greater than or equal to 1, there is this means that if k is equal to 1 or k is more than 1, then of course you have more than one self-conjugate elements. So you have more than one, in fact, the central elements. This means that the center of your group is containing more than one elements. That's why center must be non-trivial. Okay. So without any loss, you may assume that there are k elements which are the self-conjugate elements, and later we will see that which is what should be the exact value of k, or what should be the possible value of k, right? So we since G would have more self conjugate elements. So assume that there are k possible self conjugate elements okay. You may assume that Pm2 is equal to 1, Pm3 is equal to 1 and so on Pmk, because these are the symbols. We are not sure that what are the orders of conjugacy classes. That's why there is no problem that you may assume that Pm2 is equal to 1. Second conjugacy class is a self-conjugated class. Third conjugacy class is a self-conjugacy class, and so on. You may have k possible self-conjugate element, and you know that self-conjugate element is not containing any other element other than that self element. Okay, so suppose if possible Pm1, Pm2, Pm3, of course Pm1 is also equal to 1, is equal to so on, is equal to Pm or is equal to 1 as well, right? You may start from Pm2 because we already have supposed that Pm1 is equal to 1. So Pm2, Pm3, so on, Pmr is equal to 1 as well. Then equation 3 becomes putting in 3 we get P power n is equal to 1 plus 1 plus 1 plus 1 plus so on plus 1. This is k times k terms plus P power mk plus 1, right, plus so on plus P power mr, right? You can write like this. This is your mk and plus 1. This is your plus 1. Here you can add plus 1, or for it's because we are using the symbols, so there is no problem if you are writing here k plus 1. This is also okay. So you are getting P power n is equal to k plus summation P power mi, I will from k plus 1 to r. You see here P is dividing P power n, and also P is dividing each term under this summation. That's why to balance this equation P must also divide k. This means that P is a divisor of k, so that's why k must be P or multiple of P. This means that you must have P or multiple of P self-conjugate elements. So, and we know that self-conjugate elements are in fact the center elements. So that's why the center of a P group must contains either P elements or multiple of P elements. In either case, it is a non-trivial center, right? So by the last equation, you can write P power n minus summation I will from k plus 1 to r, P power mi is equal to k, right? Now divide left hand side. So because P divide K, this implies K is equal to PT for some integer T. If T is equal to 1, then K is equal to P, or if T is any other integer, T maybe any other integer, right? Of course, T is some positive integer because P is a divisor. Right, this means that there are P or multiple of P self-conjugate elements. This means that there are P or multiple of P self-conjugate elements and the self-conjugate elements are the central elements hence center of G, where G is a P group, contains more than one elements. Center of G contains P or multiple of P elements, so it is non-trivial. Okay, you can check that center of every finite P group is non-trivial. We have a very important result which we will use frequently in our next theorems, namely Cauchy's theorem and Taylor's theorem. Okay, thank you very much. Allah Hafiz.